On the night of the 1st of September, 1859, observers across North America and Europe reported a sky that defied expectation. Long after sunset, a diffuse crimson glow spread across the horizon, bright enough to cast faint shadows. Some believed distant cities were burning. Others thought dawn had arrived hours too soon. The atmosphere itself seemed illuminated from within. In rural communities, people stepped outside with lanterns raised, searching for the source of the strange light. Farmers stood in fields usually swallowed by darkness, now tinted red. Church bells rang in certain towns, rousing residents who feared catastrophe. The sky shimmered silently, and the stillness beneath it felt heavy and unfamiliar. Ships at sea recorded the phenomenon with unease. Mariners accustomed to navigating by starlight found the heavens transformed. Compass needles quivered unpredictably, though no visible storm disturbed the waters. Officers entered careful notes into their logs, aware that something uncommon was unfolding beyond ordinary weather. Telegraph operators, working late in dimly lit offices, noticed subtle irregularities in their instruments. Needles flickered without command. Circuits behaved unpredictably. At first, the disturbances were dismissed as minor faults. Yet the timing coincided with reports of luminous skies, linking ground and firmament in ways few yet understood. The glow intensified in waves, surging and receding like a tide of light. Curtains of color rippled across the heavens, folding into arcs before dissolving again. Witnesses described crimson veils and pale streaks that moved without wind. It was neither lightning nor cloud, but something vast and strangely ordered. In regions far south of the usual auroral boundary, observers struggled to interpret what they were seeing. Newspapers later collected testimonies from the Caribbean and parts of Central America, where the phenomenon was almost unknown. Such visibility challenged established assumptions about the limits of auroral display. Scientific institutions began receiving telegrams describing the spectacle. Reports varied in detail yet agreed in tone. The event was extraordinary. No immediate explanation presented itself. Atmospheric optics, volcanic dust, electrical anomalies, each hypothesis failed to account for the scale described. Throughout the night, the illumination ebbed and returned, as if governed by an unseen rhythm. Those who remained awake sensed structure within the motion, a coherence hinting at forces operating far beyond any local disturbance. Yet the source remained invisible. By dawn, as the colors faded and daylight resumed its dominion, a question lingered. The earth had not burned, nor had cities fallen. But the sky had spoken in a language few could interpret. The origin of the spectacle lay 93 million miles away. On the morning of the 1st of September, 1859, hours before the strange illumination that would later spread across the night sky, Richard Carrington climbed to his private observatory in Redhill, Surrey. The air was steady, the sky clear, and the sun rose without visible disturbance. A meticulous amateur astronomer, Carrington prepared his instruments with habitual precision, unaware that his routine observation was about to enter scientific history. Inside the modest dome, sunlight passed through a carefully aligned telescope and was projected onto a white screen. Carrington did not look directly at the sun. Instead, he traced the dark blemishes known as sunspots with pencil and ruler. The projected disk drifted gradually as the Earth rotated, and he corrected the apparatus with measured, practiced movements. Solar observation in the mid-19th century was disciplined yet constrained. Photography remained experimental, and most data depended upon careful hand-drawn records. Carrington had devoted years to charting the movement of sunspots, searching for recurring patterns in their migration across the solar surface. His notebooks revealed cycles, though their broader implications remained uncertain. As he sketched a clustered group of spots that morning, a sudden brilliance appeared within one of the darker regions. Two intensely bright patches formed, sharply defined against the solar disk. Carrington later described them as dazzling. Their luminosity was so unexpected that he briefly considered whether stray light from Earth had entered the instrument. He stepped back from the telescope, suspecting reflection or mechanical fault. The room itself remained unchanged. No cloud crossed the sky, and no disturbance altered the projection. Returning swiftly to the eyepiece, he confirmed that the luminous forms persisted, shifting slightly over the sunspot group with unmistakable coherence. The phenomenon lasted only a few minutes. The bright areas contracted and vanished as abruptly as they had appeared. Carrington recorded the time with deliberate care, noting the observation precisely in his journal. Though he did not yet understand the mechanism, He recognized that the event differed from any solar variation he had previously documented. Elsewhere, another observer, Richard Hodgson, independently witnessed the same eruption. 2 telescopes, 2 careful observers, and the same fleeting brilliance upon the Sun's surface. The coincidence strengthened the credibility of the sighting. It was not illusion. Something physical had occurred within the solar atmosphere. At that moment, neither man connected the solar flash with the luminous skies that would be reported hours later. The connection was invisible. The Sun, though studied, was still regarded as distant and largely self-contained. Changes upon its surface were treated as astronomical curiosities, not as agents capable of disturbing conditions on Earth. Yet Carrington's timed notation would prove decisive. His careful documentation established the first recorded observation of what would later be termed a solar flare. Unintentionally, he had captured the beginning of a chain of events already propagating outward through space, moving toward a planet unaware of the process unfolding above it. When Carrington recorded the sudden brilliance upon the Sun, he had witnessed a phenomenon not yet understood in physical terms. The solar surface was not a tranquil sphere but a dynamic region shaped by intense magnetic forces. What appeared as a brief flash was in fact a rapid release of energy stored within stressed magnetic fields, invisible to 19th-century theory yet measurable in consequence. A solar flare occurs when magnetic lines near sunspot regions abruptly reorganize, converting stored magnetic energy into radiation and accelerated particles. In 1859, the study of magnetism was advancing, yet the Sun's magnetic architecture remained largely theoretical. Carrington could describe what he observed with care, but he lacked the conceptual framework required to explain its origin. The bright patches he saw were not simply areas of increased light, they signified a surge of electromagnetic radiation. Within minutes, energy propagated outward from the solar atmosphere across the spectrum. Visible light reached Earth in just over 8 minutes. Yet another component, slower and more materially consequential, followed behind it through interplanetary space. Accompanying the flare was a coronal mass ejection, a vast expulsion of plasma intertwined with magnetic field lines. This expanding cloud carried charged particles and embedded magnetic structure away from the Sun. Though unseen by contemporary observers, it possessed the capacity to disturb the magnetic environment of any planet along its path. Under typical conditions, such ejections require several days to traverse the distance between Sun and Earth. The 1859 eruption, however, traveled with unusual speed. Earlier solar activity may have altered the interplanetary medium, reducing resistance and allowing the plasma cloud to advance more rapidly than usual. The transit time was dramatically shortened. Approximately 17 hours after Carrington's observation, the advancing plasma encountered Earth's magnetosphere. The planet's magnetic shield, ordinarily deflecting solar wind, absorbed the impact unevenly. Magnetic field lines were compressed and displaced. The structure surrounding Earth began to oscillate under external pressure. At ground level, no explosion announced the arrival. There was no audible shockwave, no visible disturbance in the lower atmosphere. Yet instruments sensitive to magnetic variation registered abrupt and extreme deviations. The disturbance was geomagnetic in nature. Energy initiated at the Sun was now coupling directly with Earth's own magnetic field. The connection between solar eruption and terrestrial effect was not immediately recognized. Astronomers examined the Sun. Telegraph engineers monitored circuits. Meteorologists studied atmospheric conditions. Each discipline operated within its own framework. The event transcended those boundaries, linking them through an electromagnetic chain not yet conceptually unified. By the time night returned to parts of the globe, the consequences of that morning's flare were becoming evident. The same energy Carrington had traced in pencil was now interacting with compass needles, telegraph wires, and the upper atmosphere. The Sun had not merely brightened, it had altered the magnetic balance of a planet. Between eruption and impact, the expelled solar plasma traversed nearly 93 million miles of interplanetary space. The region between Sun and Earth was not empty but structured by magnetic fields and sparse charged particles. Through this medium, the coronal mass ejection advanced as a coherent magnetic structure, carrying embedded tension accumulated within the solar atmosphere. Under ordinary conditions, Earth's magnetosphere functions as a resilient barrier. It diverts most incoming solar wind around the planet, guiding charged particles along field lines toward high latitudes. The balance between solar pressure and terrestrial magnetism is dynamic yet stable. Only under exceptional strain does that equilibrium begin to distort. The 1859 ejection appears to have carried a strong southward magnetic component. This orientation enabled efficient magnetic reconnect ion with Earth's northward field. Field lines linked, broke, and reconfigured. Through this process, solar energy was transferred directly into the magnetosphere, intensifying geomagnetic disturbance beyond typical limits. As the shock front compressed the magnetosphere, electrical currents intensified within the ionosphere. Charged particles followed magnetic field lines toward lower latitudes than usual. The auroral oval expanded equatorward. Regions rarely exposed to polar light were suddenly within reach of energetic precipitation from space. At the same time, rapid fluctuations in Earth's magnetic field extended downward to the surface. Conductive materials became pathways for induced currents. Long iron telegraph wires, strung across continents and grounded at intervals, formed extensive linear conductors embedded within a changing magnetic environment. Observatories equipped with magnetometers recorded abrupt and extreme deflections. Instruments traced oscillations well beyond normal variation. To those monitoring the data, the readings indicated a global magnetic disturbance. Yet the causal chain linking Surrey's morning observation to these terrestrial deviations was not immediately understood. The compression of the magnetosphere also altered the distribution of charged particles in near-Earth space. Although the lower atmosphere absorbed most harmful radiation, the electromagnetic disturbance was sufficient to disrupt sensitive instruments and electrical systems. Earth's protective envelope remained intact, but it had been driven into an extreme configuration. What had begun as a brief solar flash now manifested as systemic instability. In less than a day, energy released at the Sun had traversed interplanetary distance and engaged directly with the technological infrastructure of an industrializing society. Telegraph lines, compasses, and magnetometers became components in a planetary-scale interaction. By the evening of the 1st of September and into the early hours that followed, geomagnetic conditions intensified further. The sky would ignite again with auroral light, and the world's expanding electrical network would respond in ways its designers had not anticipated. The disturbance was no longer confined to scientific instruments, it was entering daily life. By the time darkness returned across large portions of North America and Europe, telegraph offices were experiencing disturbances that could not be dismissed as routine malfunction. Operators reported unexpected surges of current traveling along their lines. Sparks leapt from metal contacts. Paper strips smoldered or ignited. A technology that symbolized modern progress had become electrically unstable. Mid-19th century telegraph systems relied upon long iron wires suspended between wooden poles, grounded periodically and powered by chemical batteries. Some lines extended for hundreds of miles without interruption. When Earth's magnetic field fluctuated rapidly, electric potential was induced along these conductors, turning communication lines into unintended receivers of geomagnetic energy. Operators attempting ordinary transmissions found their signals overwhelmed by uncontrolled impulses. Indicator needles swung without key input, then stalled, then reversed direction. In several stations, batteries were disconnected in an effort to stabilize circuits. Yet messages continued to pass intermittently, driven solely by currents induced by the geomagnetic disturbance. Reports circulated of telegraph clerks receiving electric shocks from metal components. Keys grew warm beneath their fingers. Sparks ignited paper tape where it brushed exposed contacts. Engineers inspected wiring and insulation, uncertain whether atmospheric electricity, faulty grounding, or equipment failure lay behind the phenomenon. The disruptions were not confined to a single city or region. From Boston to New York, from London to continental Europe, similar behavior was documented. The simultaneity suggested a broad magnetic disturbance rather than isolated technical defect. Telegraph lines, stretched across landscapes, had become linear antennas embedded within a changing geomagnetic field. Some operators, recognizing the unusual origin of the current, experimented with caution. By disconnecting their batteries entirely, they attempted to use the induced electricity itself to transmit messages. In certain cases, communication persisted briefly without local power sources, sustained by the storm's geomagnetic energy. For a civilization only beginning to understand electricity, the implications were sobering. The telegraph had compressed geography, allowing information to move almost instantaneously across nations. Now that same infrastructure revealed structural dependence upon environmental stability extending far beyond weather or terrain. Newspapers gathered accounts in the days that followed, combining technical description with measured astonishment. The electrical age had not collapsed, but it had been forced into visible vulnerability. An external influence had entered wires and instruments without permission or warning. As telegraph clerks extinguished minor fires and restored cautious operation, the skies above continued to glow. The network had not merely malfunctioned, it had conducted energy initiated at the sun. What began as a brief solar flash was now measurable in iron lines spanning continents, currents driven by a star. While telegraph lines carried induced currents across continents, the upper atmosphere produced a spectacle of unusual scale. Curtains of light unfolded across the night sky in colors seldom observed at such latitudes. Crimson dominated the horizon, interwoven with pale green and occasional white streaks, shifting in broad arcs that rose and fell with measured regularity. Auroras were familiar in northern regions, yet the displays of September 1859 extended far beyond their customary boundaries. Observers in Cuba, Jamaica, and parts of Central America described luminous skies resembling distant fires. In Rome, the glow was mistaken by some for a blaze beyond the city walls. The phenomenon had crossed latitudes where auroral light was rarely recorded. The movement of the light possessed discernible structure. Rays converged toward magnetic zeniths, then dissolved into diffuse glows before reforming elsewhere. There was no thunder, no wind, no audible sign of disturbance. Those watching perceived pattern rather than chaos, though the mechanism lay hidden high above the visible layers of the atmosphere. Scientific institutions received descriptions from multiple continents within days. Despite regional variation in color and intensity, the reports shared consistent characteristics. The geographic distribution suggested a coordinated response within Earth's magnetic environment rather than isolated atmospheric anomaly. The equatorward expansion of visible aurora implied an extraordinary disturbance in geomagnetic configuration. Charged particles, normally confined to high latitudes, were now being guided along magnetic field lines toward regions unaccustomed to such precipitation. The auroral oval had widened dramatically, reflecting the strain imposed upon the magnetosphere. In certain locations, the light was sufficiently bright to permit reading without artificial illumination. Farmers reportedly prepared for early labor, misled by the intensity of the glow. The distinction between night and dawn blurred, not through the rising of the sun, but through energy deposited into the upper atmosphere from space. Artists and chroniclers attempted to capture what they witnessed in sketches and written accounts. Their descriptions emphasized color, motion, and reach, yet struggled to convey scale. The display did not hover over a single horizon, it spanned entire skies, arching overhead and descending toward unfamiliar directions. For observers unaware of Carrington's morning observation, the aurora appeared as an isolated terrestrial mystery. Yet the simultaneity of atmospheric illumination and telegraph disruption suggested connection. The sky and the wires were responding together, both shaped by fluctuations in Earth's magnetic field driven from beyond the planet. As the light gradually diminished toward dawn, familiar darkness returned. But the range of observation, from northern Europe to near-equatorial regions, confirmed the disturbance had been planetary in scope. The atmosphere had revealed its sensitivity to forces originating far beyond its thin boundary, and the evidence was written in light. The events of September 1859 demonstrated a fact not yet fully articulated at the time. Earth's atmosphere and its emerging technological systems were magnetically coupled to the sun. They were not isolated environments, but components within a larger electromagnetic structure. To understand what occurred, one must follow the sequence from solar eruption to terrestrial current. Earth is encased within a magnetic field generated by convection within its molten iron core. This field extends outward, forming the magnetosphere, a protective cavity that deflects most solar wind. Under ordinary conditions, incoming charged particles are channeled toward polar regions, where interaction with atmospheric gases produces auroral light. During an extreme solar storm, external magnetic pressure increases sharply. If the orientation of the incoming field opposes Earth's own field, magnetic reconnection can occur. Field lines break and realign, permitting energy to enter the magnetosphere efficiently. The process transfers solar energy directly into Earth's magnetic system. Once injected, that energy drives intensified electrical currents within the ionosphere. The auroral oval expands, and geomagnetic conditions fluctuate rapidly. Regions typically shielded from energetic particle precipitation become exposed. The visible aurora is only one expression of a broader electromagnetic restructuring. At ground level, the same fluctuating magnetic environment induces electric potential within conductive materials. This is the principle of electromagnetic induction. A changing magnetic field generates current in nearby conductors. Telegraph wires stretched across continents became extended receivers within a dynamically shifting field. In 1859, electrical infrastructure was limited compared with modern standards. Yet even this early network revealed dependence upon magnetic stability. The storm did not create electricity ex nihilo, it altered the distribution of existing electromagnetic energy, forcing systems into unintended behavior. Scientists of the period began assembling evidence from multiple domains. Magnetometer readings, auroral observations, and telegraph disruptions formed a coherent pattern. Although the physical mechanism was not yet fully described, the correlation between solar activity and geomagnetic disturbance became increasingly difficult to dismiss. What distinguished the Carrington storm was not simply the presence of aurora, but the scale and simultaneity of its effects. Within hours, solar activity had influenced atmospheric light, magnetic instruments, and electrical infrastructure across vast distances. Separate systems responded to a single external driver. The implication was structural rather than episodic. If solar activity could alter magnetic conditions so rapidly, then technological society, however early in development, was exposed to a variable beyond terrestrial control. The industrial world had extended wires across landscapes under assumptions of stability. The storm revealed that stability itself depended upon forces originating 93 million miles away. In 1859, the world's electrical infrastructure consisted primarily of telegraph lines and isolated instruments. Today, the scale of dependence upon electromagnetic stability is incomparably greater. Satellites orbit continuously above the atmosphere, guiding navigation, transmitting communications, and synchronizing financial systems. Much of modern society relies upon uninterrupted electrical continuity. A geomagnetic storm comparable to the Carrington event would interact not only with ground-based conductors but also with orbital systems. Satellites exposed to intense solar radiation may experience component degradation, communication disruption, or increased atmospheric drag due to upper atmosphere expansion. The consequences would extend beyond visible auroral displays. High-voltage power grids, spanning continents, are particularly sensitive to geomagnetically induced currents. Long transmission lines can channel induced electric potential into transformers, where internal heating may exceed design tolerance. Unlike 19th-century telegraph equipment, modern transformers are complex, costly, and not rapidly replaceable. Navigation systems dependent upon satellite timing signals are vulnerable to ionospheric disturbance. Aviation routing, maritime positioning, emergency coordination, and digital infrastructure rely upon precise synchronization. Severe geomagnetic fluctuation could introduce signal distortion and temporary loss of accuracy across wide regions. Financial networks and data centers require continuous timing alignment to maintain transaction integrity. Even brief electrical instability can propagate through interconnected systems. What in 1859 produced sparks and minor fires could, under contemporary conditions, generate cascading operational disruption across sectors dependent upon stable power distribution. Space agencies now monitor solar activity continuously. Observatories track sunspot evolution, measure magnetic complexity, and detect coronal mass ejections in near real time. Early warning systems provide limited preparation windows measured in hours. Mitigation strategies exist, yet structural vulnerabilities cannot be entirely eliminated without systemic redesign. Historical and statistical studies indicate that extreme geomagnetic storms recur irregularly but plausibly within century-scale intervals. The absence of recent catastrophe does not imply long-term immunity. It reflects probabilistic spacing rather than permanent protection from high-magnitude solar events. In 2012, a powerful solar eruption crossed Earth's orbital path shortly after the planet had moved beyond that position. Had the alignment differed by approximately 1 week, the resulting geomagnetic disturbance might have approached Carrington-level intensity. The event served as a reminder that such solar activity remains physically possible. The central question is therefore not whether the Sun retains the capacity to produce extreme storms, but whether modern infrastructure is engineered with sufficient resilience to withstand them. The technological web linking continents has expanded dramatically since 1859. Its durability under severe geomagnetic stress remains a matter of ongoing assessment. The Carrington event was not an isolated anomaly but part of a broader pattern of solar variability. Subsequent decades have recorded geomagnetic storms of considerable intensity, though none have equaled the estimated magnitude of 1859. Each occurrence reinforces the understanding that extreme solar behavior is inherent to stellar dynamics rather than exceptional deviation. In May 1921, a powerful geomagnetic storm disrupted telegraph and railway signaling systems across parts of North America and Europe. Communication facilities reported electrical fires and signal failures. Though less globally expansive than the events of 1859, the disturbance demonstrated that technological systems remained susceptible to magnetic fluctuation. March 1989 provided a more contemporary illustration. A geomagnetic storm induced currents within the Hydro-Quebec power grid, leading to transformer damage and a widespread blackout affecting millions. Within 90 seconds, much of the province lost electrical supply. The modern era experienced a measurable solar consequence within an interconnected power network. Advances in space-based observation have since improved detection and forecasting. Satellites such as SOHO and SDO monitor solar surface activity and coronal mass ejections continuously. Yet detection does not equate to prevention. Warning intervals may be limited, and the effectiveness of response measures varies by infrastructure design. The 2012 near miss underscored statistical reality. A substantial solar eruption passed through Earth's orbital position shortly after the planet had moved beyond that location. Analysis indicates that, had alignment coincided, the resulting geomagnetic impact might have approached the intensity associated with 1859. Probability assessments suggest that Carrington-scale events may recur within century-scale timeframes, though precise forecasting remains impossible. Such estimates rely upon limited historical records and indirect evidence. Nonetheless, they indicate that extreme space weather belongs within the range of plausible future scenarios. In response, governments and power authorities have implemented mitigation strategies, including grid hardening, transformer design modifications, and monitoring protocols. These measures reduce exposure but do not eliminate systemic interdependence across energy and communication networks. Unlike terrestrial hazards, solar storms cannot be confined to a single region. The magnetosphere is planetary in scope, and geomagnetic disturbance can influence multiple continents simultaneously. Effective resilience therefore requires coordination across national boundaries and industrial sectors. The Carrington event endures as a benchmark rather than a relic. It defines the upper limit of documented solar-terrestrial interaction. Each subsequent disturbance and each narrowly avoided alignment is measured against it, reinforcing a consistent conclusion. Solar activity remains capable of imposing large-scale magnetic reconfiguration upon Earth. In the years following 1859, Richard Carrington continued his astronomical observations, though the full significance of what he had recorded emerged gradually. The brief flash he documented was not an isolated curiosity but a signal of solar capacity. It demonstrated that events upon the Sun could extend beyond observation and produce measurable consequence on Earth. Earth orbits within a magnetic relationship it does not govern. Solar cycles rise and fall over intervals of roughly 11 years, increasing and decreasing the frequency of sunspots and eruptive activity. During periods of maximum activity, the probability of flares and coronal mass ejections increases, though precise timing remains unpredictable. Modern civilization now depends upon extensive conductive systems, power grids, undersea cables, satellites, navigation networks, and data centers. These structures operate under assumptions of electrical continuity. The Carrington event demonstrated that continuity can be interrupted by processes originating far beyond terrestrial weather or geology. The Sun is neither adversary nor ally, it is dynamic. Its magnetic fields twist, store energy, and occasionally release that energy in abrupt reconfiguration. Most eruptions disperse into space without intersecting planetary environments. A fraction, under specific orientation and timing, couple directly with Earth's magnetic field. What distinguished 1859 was not merely intensity but alignment. The magnetic orientation and velocity of the ejection enabled efficient energy transfer into the magnetosphere. Such alignment is not constant, yet it remains physically possible. Stellar physics does not adjust itself to technological expectation. Preparedness therefore requires structural humility. Monitoring, modeling, and infrastructure reinforcement reduce exposure but cannot remove it entirely. The lesson of Carrington is not alarm but recognition. Complex systems operate within a broader cosmic environment whose variability cannot be engineered away. When observers described crimson skies in 1859, they witnessed both beauty and disturbance. The same auroral light that illuminated fields and harbors also induced currents in iron wires. Aesthetic spectacle and electrical instability were expressions of the same electromagnetic interaction. In archival collections, Carrington sketches remain, graphite traces of sunspots upon a projected solar disk. The marks appear modest, almost understated. Yet within them lies the first recorded observation of a solar flare whose effects extended from the surface of a star to the surface of a planet. The sky that should not have existed did exist. It revealed that industrial civilization resides within a stellar system, not apart from it. The warning was quiet, written in light and magnetism. It remains, embedded in the historical record, as both demonstration and reminder.